I was not sharing the screen the entire time. Oh no, oh no. Okay, anyway, let's go back. No one let me know. Anyway, it's fine. So we're gonna be talking about probability, entropy, and more. Thank you, Tarkun, for following. So we're going to be talking about probability, entropy, and more. And the first equation that we're going to be discussing is the probability of disjoint events. So this equation that we have here, it looks a little bit more complicated than we'll actually write it as. But in essence, we're going to be talking about events, what are disjoint events, what are events as a whole, how do I categorize them, and a little bit on defining probability, at least for our purposes. And we're also going to be talking a little bit on Bayesian updating and this sort of interpretation of probability. Yes, so that's going to be our first... Oh, my presentation is being weird. Okay. Anyway, let me just restart my presentation. Sometimes it starts being weird like this. But anyway, so a little bit on just notation and definition. So what is an event? I'm sure most of you guys probably saw it in school or high school, but here we define as events as a subset of outcomes in the set of all possible outcomes. So there's all the things that can happen, so all the possible outcomes, and an event is a subset of these outcomes. So this is just a subset of outcomes of things that can happen. And when I have two events, A and B, they can be mutually exclusive, meaning that they don't share anything in common, and this makes them disjoint. Okay? And the opposite of disjoint, and the definition is that the space shared, basically the subset shared between A and B, is the null set or the empty set, which is a set that contains nothing. So these guys are not touching at all anywhere. Nothing that is contained in A is contained in B. So that would be, for example, think of an example on the fly. Like how many birds are fish, for example. Birds are not fish, so the group of birds is not in the group of fish and don't share anything in common. But they can also be non-mutually exclusive and they share something, so the intersection of them is not the null set, is not an empty set. We have something that intersects between the two. But we're going to mainly be talking about disjoint event, meaning the ones that don't share anything together, and that makes things quite a bit simpler, actually, to calculate their probability. So now that we've discussed what's an event, so a subset of outcomes, we define what's a disjoint event, so an event that doesn't share anything with other events that we're going to be discussing. Penguins and flying fish, close, but not quite. Now we're going to define probability, which we're definitely not going to be doing right now because defining probability is actually a very difficult, complex whole area of study. But probability, whether we can define it or not in very simple words, it can be pretty intuitively described. And we're going to discuss a little bit on the interpretations of probability. So what probability actually means in, let's say, more physical terms. So we have, for example, one interpretation of probability is known as the frequentist probability. And this defines probability as, it defines the probability of a particular event as basically the frequency of the outcome given that I repeat a specific trial infinitely many times. So for example, if I go and I ask Harhi, are you interested in aliens? And she always replies yes. I assume I could ask for all infinity until the end of times that yes, she is interested in aliens, for example. So it's something that I assume that until the end of times, it's gonna be this. So for example, the example that is often cited is if I flip a coin that is not skewed towards towards heads or tails, it's completely unbiased. If I flip it infinitely many times, I expect that half of the times will be heads and half of the times will be heads. So this is a good example of what would be a frequentist probability interpretation. Yes. And then another example of how to define probability or to interpret a probability is what's known as Bayesian probability, which proposed by this guy, statistician, Thomas Bayes. And it's described as a degree of belief or a subjective probability given some pre-existing knowledge that I have on my system. So this can be, for example, given that I have a coin and it's completely unbiased and I have two faces, I expect that I will get one of them half the time and the other one half the time, without needing to go into this infinitely many trials interpretation. But at the same time, you reach the same conclusion. But this allows for testing hypotheses and updating when new information becomes available, which we're going to do in a little bit. So when you add new information, you can adapt to this new information. So then I say, actually, this coin now has a little scratch, and maybe it will make it so that 5% more of the time it will flip to heads or something like that. So it can help you update according to new knowledge that is introduced. And this probability, he relates it to something known as likelihood, and likelihood is the probability, so a local probability of an observation for a particular hypothesis. So basically a local probability for a hypothesis. So just a little bit of two different interpretations where we can kind of reach a similar conclusion. Just one kind of allows for a little bit more updating and introducing new knowledge, and it doesn't really rely so much on this infinitely many trials interpretation. So now that we know what probability is, we know about disjoint events. Now I have a big set of disjoint events, and this set I'm calling just S, and all the probabilities of the disjoint events by definition need to add up to 1. So they add up to 100%, because that would be the total probability of my set of possible outcomes. So I am 100% likely to get an event out of the set of all possible events, where all the events are here denoted as E and some sort of natural number, E1, E2, E3, E4, and so on. Now, I express my probability now just in terms of P of S, so the probability of my set of outcomes. But how do I express this probability in terms of the total number of events? So just a little bit of intuition. So a little bit of intuition. By summing up all the possible events, I get the total set of events. So by summing up all the probabilities of all of the events, I will get the total set of my probabilities. But this, like we mentioned, this is only the case where the events don't overlap, because if they overlap, then we would be summing a particular space twice. So which we'll look at in just a second. But yeah, so for the case of disjoint event, we can just add all the probabilities of each of the individual events, and we arrive at this equation, which is the one given in the opening. So the probability of the union of all my events, which is S, is the union of all my events, is equal to the sum of each probability of each separate events separately because they are disjoint. But this is not valid if the events are not disjoint. Yes, Frolic, I did not want to explain likelihood as probability. I just mean that they are related to each other, and that likelihood is more so seen as a local probability, I guess you could say, or like a local description for a probability given a particular hypothesis, but not directly, like a frequentist probability. But yeah, of course, this is more complicated than what I want to explain right now. So so I'm just saying that for Bayesian probabilities, you typically will hear a lot of the times this word likelihood, and this relates to, in particular, a particular hypothesis and not just a general probability. So that's why you hear this word likelihood so often in relation to probability. But I know that it has its own mathematical definition and so on. I did not want to get into that. So I hope it's understandable for this sake. But yeah. So we have our probability of disjoint events. So just to reiterate, for disjoint event, meaning events that don't share any subsets of events with other events, we can actually just sum all the probabilities individually to get the total probability of all of my events. And this probability, when we factor in all of the events, should add up to 100, because that would be the probability that I get an event from the subset of all possible events. So the probability of the union of all my events is equal to the probability of S, and this is the sum of each individual probability for each event. But what if they overlap? So it gets a little bit more complicated when they overlap. I just bring up the example of when we have two events, so event A and event B. And like I said, we have to factor in that there's this individual or this union or intersection between both of my events. So I need to subtract it, because otherwise I would basically be counting it twice. So for the example that I have, the probability of getting A or getting B or getting both of them, I need to do the probability of A plus the probability of B minus this little bit in between that I need to subtract. Otherwise, I would be counting it twice. And as you get more events that overlap, this equation just becomes more and more complicated. So I just thought I would explain the example for 2. So yeah, so we have to avoid double counting by this subtracting the intersection. So now a little bit more on this Bayesian updating and what this is even useful for. Most of what I will discuss was actually inspired a little bit by a video that I watched when I was in like my first year of college, which was taken by 3 Blues 1 Brown. I'm sure anyone that studied any STEM subject will have seen his videos. He makes really interesting content on math and so on. And his example was motivated by some research done by Nobel laureates Daniel Kahneman and Amos Tversky. I'm sorry, I probably insulted their names. I don't know how to say them. But yeah, so everyone knows 3 Blues 1 Brown. I just took this example that he did, really stuck with me, so I wanted to just incorporate it into this. So I asked you guys on Twitter, Harhi is energetic and eccentric. She's confident and has an intense curiosity about the supernatural. She's stubborn and likes being a leader. Is Harhi more likely to be a retail worker, or is she more likely to be an astronomer? So the answers, for the most part, will depend on what you consider this information, what you take this information as to meaning what. So I asked the question and I got 60.9% said retail worker and 39.1% said astronomer. So let's see. So what did people think? So just in general, for the most part, people really focused on the characteristics that I said, but we also had some people that brought up some outside knowledge. For example, this answer said a retail worker because of the state of the economy currently. So factoring some new knowledge. Then some other answers, she would have, if she worked in retail, she would have more time to research stuff on her own, or neither, because neither profession rewards people like her, so focusing on the characteristics. Then astronomers would be, it would be more adequate because she really likes aliens, but she would get bored pretty quickly and maybe give up. So a lot of people really focused on just her as a person. She's a perfect example of a genius who would rather pursue things that she likes on her own. She's an astronomer working, she would be an astronomer working in science because of her qualities. So I feel like people really took in the qualities. I just had one answer by someone that I'm sure also had this example somewhere along their career, which said that she would most likely be a retail worker because there are a lot more retail workers than astronomers. By a large order of magnitude. So meaning that even if a lot of these astronomers had these qualities, there would be so many retail workers that a larger number of them probably have these qualities. So we had a little bit of answers all over the board, but in general, most of the people focused on the qualities that I presented. So yes, you can do that. However, the basically the understanding of this problem is to know what to do when we find more information on the matter. And for this, we use Bayes' theorem. So in here we have, I'm already putting it in the names of the things that you would, to understand it. So this is Bayes' theorem, and what it tells us for our particular example is this is the probability of a person being an astronomer given that they possess these particular qualities that I described. And then here, this would be the probability that someone is an astronomer given these, with these qualities, given these qualities. A is simply astronomer, just being an astronomer, and B is possessing these qualities. So B here is basically our hypothesis, which is having these qualities, or is maybe more tied to being an astronomer, maybe not. And A is just being an astronomer. But yeah, just to read it a little bit simpler, I put it in actual words for our particular example. Yes. So now we introduce new information. So we had people mostly focusing on just the qualities themselves, but now we're going to talk a little bit about how many astronomers and how many retail workers there are. So I took this data from Data USA, and it says in there that 16.2 thousand people in America work in, I could not find one just for astronomy, so I included astronomy and physics. And then 3 million people work in retail. So now we have a little bit more information of how many people are actually working in these two particular fields. So if we start thinking like, what percentage of these workers actually have these qualities? What percentage of them are confident, curious, leaders, etc.? Let's be really mean to retail workers and say that only 0.5% of them are confident, curious, and leaders, which is being a little bit too mean, I think, but maybe, I don't know. But let's be really nice to astronomers and physicists and assume that 50% of them have these qualities. So 50% of them share these qualities with Haruhi, and only 0.5% of retail workers actually share these qualities. That leaves us with about 8.1 thousand astronomers and physicists and about 15,000 retail workers. So we're introducing a little bit of new knowledge. So we actually have a lot less people than we initially thought. We actually only really need to mainly think about the people that share these particular qualities. Yes. So now we update with new information. So we have the probability of Haruhi being an astronomer would be 50%, which is, like we said, the probability that an astronomer shared these qualities, times the number of astronomers, divided by the numbers of astronomers and retail workers that have these qualities. So basically adding these two numbers of 8.1 thousand and 15,000 retail workers. So we add all the people that have these qualities and we divide the total number of astronomers by the probability that they have these qualities, and we arrive at a probability of about 35% that Haruhi is an astronomer, which is actually surprisingly close to what you guys voted. And these numbers with the 50 and the 0.5%, I kind of just made up, and it ended up matching, and I thought, okay, I'll just leave it like that. But yeah, so as I just said, if I change these percentages, if I go and ask a bunch of retail workers, do you have these qualities? And then maybe I extract some other value of how many of them share these qualities, this probability is going to change a lot. So it's a result really dependent on the available information that we have. So, so basically this Bayesian updating is very useful for updating with new information that becomes available. But at the same time, even though it's very useful, it largely depends on the quality of this information at the same time, which, for example, for this, the quality is not the best quality because I just took some statistics that you can find online that are maybe not that accurate, and then I just made up some numbers to get some value out. So the result will depend a lot on the available information. So don't take this 35% as anything too seriously, because I just made up these percentages. But yeah, so are there any questions until now? I'm sorry that I haven't read the chat so much. Just there was so much information to fly through. But yeah, so any comments, any questions? I will maybe read up a little bit on what you guys said. So we had my feeling when I have to explain sigma algebras and mapping to properly define probability. Yes, this was not our goal for today. I really just wanted to give a little bit of an intuitive understanding of probability. And in particular, just this updating intuition and updating interpretation. Let's see. Team retail. She would be fired from both jobs. Honestly, probably. I refused to be part of the experiment, so I did not vote. And yeah, Bayes was the real sigma among the algebras. So true. Yes. So clear so far. It's not too mean to retail workers. Yeah, so I mean, like I said, maybe retail workers are worse, maybe they are better. I don't know. Maybe we really need to update that probability. But yeah, so I think if we're clear on probability, we're going to continue talking about probability a little bit, but now in the context of Shannon entropy, which is actually something that was introduced, I don't think directly in mathematics, but was actually introduced in the field of computer science, in particular in information theory. Yes, remember when that guy stole my KFC and they did nothing? So true, so true. Also, just a side note, actually there was a little bit of what would you call it? A little bit of what I found, a little bit of an oddity in the data that I found for the number of retail workers was in particular that they split up the profession the profession of being a cashier from the profession of being a retail worker, where I feel like, I don't know, like maybe it's just me, but I feel like, can you be a retail worker without being a cashier? I don't know. But anyway, so they do split these two values up. If we were to, write it a little bit differently, I took their word for it. But yeah. Yeah, if some people work both jobs, I have no idea, because it seems to me that they completely split it, at least in this data that I found in particular. So I'm not sure how they categorize it in America, but it seems like they split the jobs into two separate jobs. Anyway, so Shannon entropy. So Shannon entropy, this equation actually took me a little bit of time to think about what the heck this is, because I was like, this looks like another Hamiltonian, but I have never seen a Hamiltonian that looks like this. And then I was like, oh wait, has to be the Shannon entropy. So I believe I am 99.9% sure that this has to be Shannon entropy, but Harhi's face was covering the equation most of the opening, so if anyone has any idea of what else this could be, please let me know, but I'm pretty sure this should be Shannon entropy. Anyway, so we have we have Haruhi, and she's gonna make a bet with us. So Haruhi wants to know how many people have watched her show, and she bets $1 for every person who has watched the show. So if they have watched the show, she gets $1. If they have not watched the show, she has to pay us $1. So how much money do you think that Haruhi will win or that she will lose? So let's talk about it. We can find how much money that Haruhi may make or lose by looking at the expected value. And for the sake of this, I asked you guys on Twitter if you guys have watched the show The Melancholy of Haruhi Suzumiya. So we had 62.9% of people said yes, and then we had 37.1% of people who said no. So it seems like a lot more people said yes than no. And we're going to be taking these two voting percentages as the probability in the population of my followers that they have watched Haruhi or that they have not watched Haruhi. Obviously, this probability would depend greatly on what population you're taking. If you take the population of, let's say, North America, it would probably be more so somewhere in the 1% have watched Haruhi. But if you maybe take somewhere like Japan, maybe it's a little bit upwards in the 10, 20% or so on. But since a lot of my followers on Twitter like Haruhi, we have 62.9%. So we're going to assume this is the probability that someone in my followers likes. Let's say that this is representative of the probability that people in my following have watched Haruhi or not watched Haruhi. So how do I know how much money Haruhi is making or has made? Is by calculating the expected value of the money made, which here it's the expected money made per wager. So we have up here we have two numbers, which is first of all $1 times each person who has watched Haruhi, so the number of people that watch Haruhi, and then minus, so we subtract the $1 times the number of people who have not watched Haruhi. So the top part should give us the total money that Haruhi makes, and then the bottom part is just to divide by the number of wagers, so the number of total people in this particular population that voted in the poll. So how do we get the number of people? We take our percentage as the probability that the particular people in the population have watched Haruhi times the total number of people, which is the 232 votes. And for this particular example, we had 146 people who have watched Haruhi and 86 people who have not watched Haruhi. So now we have our two numbers that we're going to need to calculate our amount won or our amount lost per each wager. So the expected money per wager is the number of people who have watched Haruhi times $1. We said that would be 146 times $1, $146 minus 86 people who have not watched Haruhi times $1, $86. We subtract that, we divide it by the total number of wagers, and we get that Haruhi is actually making 0.26 cents per each wager. So she is actually making money by making this bet with us. And yeah, she expects to win this much money per wager. Again, if we assume that the results of the poll are representative of the long-term probabilities of this population. But this is what's known as an expected value for this particular example. Now, to give it a little bit of a more generalized formula, this would be the formal definition of the expected value. So we have the expected value of all my x's is the sum of each x times the probability of this particular x. And its definition is basically that it's a long-term average outcome of a particular random variable. In this case, our random variable was watching Haruhi, for example, or the money made by Haruhi or wager whether they watch Haruhi or not. But yeah, I hope that makes sense. But yeah, so the important part here is that the definition of the expected value is the value itself times its probability. Okay, AdCast is heading out, so see you. Bye. The chemistry part will be very short, but I hope it'll be at least a little bit interesting. I'm sure you've already heard it, but yeah. So this is my expectation value. Expectation value is the one they use typically in quantum mechanics. I always use them interchangeably. They kind of can be used interchangeably, but the other one is more so used in a different context. But yeah, so this is our expected value. And now what does this have to do with Shannon entropy? Before we get to that, we talk about Haruhi, who just brought us some ice pops. So Haruhi is here to deliver some ice pops, and here are the ice pops. And now Haruhi says, I don't like how they look like this. Let's split them up into nice even groups. And we see our groups here we have a lot of blue ice pops and a couple of the pink ones. And here we have a lot of pink ones and just one singular blue one. So if I take one at random from each group, what do I expect? And I expect that if I take one at random from this group, I expected that it is gonna be blue because there's a lot more blue than pink ice pops. Similarly, if I take one from the other group, I would most likely expect it to be pink and not blue because there's a lot more pink ones. So yeah, so this gives a little bit of an intuition of how surprised would I be if I take something from one group and what I believe is the most likely outcome is what I end up getting. So if I get a blue one from this group, I would not be very surprised. But if I got a pink one from this group, I would be pretty surprised because there are not a lot of them. But yeah, so this has to do with surprise. So if we take this particular group, would Haruhi born... Oh, explosion. Thank you, Merauke, for subscribing. But yeah, thank you so much for subscribing. That kind of scared me for a sec. Anyway, so surprise. So would Haruhi be more surprised if she picked out a blue ice pop from this group, or would she be more surprised if she picked out a pink? She would be more surprised if she picked out a pink because there is a lower probability. So now we have a little bit of an intuition of what is pink? What is probability in relation to our surprise? So low probability, high surprise, high probability, low surprise. Not very surprising if I get a blue one from the group. So that would be the relationship between probability and surprise. Now, formally, this is given by something that looks like this, and mathematically, this is the log of 1 over p, which you can simply, by the rules of logarithm, take out a minus and just put log of p. But yeah, so our surprise depends on probability by minus the log of probability. So a little bit of an intuition check of why does this make sense? I'm not going to do like a proof or anything right here, but just to get a little bit of an intuition. For lower for higher surprises, so when we are very surprised, we have very, very low probabilities, which makes sense. If there's something that has a really low probability of occurring, I will be really surprised when it actually happens. And similarly, when the surprise is at 0, so when the surprise crosses the x-axis, we get a 100% probability. So that means that if the probability of something occurring is 100%, my surprise will be 0, because I expect that. I expect it to happen this way if there's 100% probability of it happening. So just a little bit of an intuition check of what is the surprise in relation to the probability, and the main thing is that it's given by this minus log of the probability relationship. So entropy is the expected value of the surprise. So we talked about how we calculate expected values, and the way that we calculate Shannon entropy is by putting these two ideas together. So the formula for the Shannon entropy is given by minus the log of probability times my probability, and I sum that for every particular possibility, right? So yeah, so just to digest this formula a little bit, this is the expected value of my surprise. So the surprise is the log of p times this probability p of my surprise. Okay, and now a little bit of just a physical interpretation. In information theory, for example, which is where this formula came from, entropy is given as basically the uncertainty and the disorder of a particular system. So how, so basically if we have high entropy, that means there's a lot of different outcomes that have really low probabilities. And then a higher entropy means that more information is needed to fully describe a system, because there's a lot of different outcomes that have really low probabilities. And then in a similar way, in physics, entropy is used to describe the order or disorder of a particular system. So something like a cold crystal is a lot lower in entropy because it's order, there's not as many ways and you can rearrange it. And it's just a particularly very high probability scenario. Whereas a gas in a really large room is very high entropy because it can organize itself in so many possibilities, so many probabilities, and they'll have a low chance of occurring. So you have so many possibilities with low probability. So again, just a lot of disorder, and yeah, kind of chaos, I guess, in a way you could say. So I just added this dumb joke to where Haruhi's like, I am not quirky, I'm just high entropy, roar, because she's like, oh, she disappeared and came back. But yeah, because she's like the roar XD girl from like the 2000s. But yeah, so entropy helps us quantify disorder, chaos in a particular system. And I feel like this relates to Haruhi law. Maybe that's why they chose this particular equation, because it just tells us about how much chaos, how much something is actually organized, orderly, nice, etc., or how crazy it is, basically. But yeah, so let me know if there are any questions thus far. After this, I just have a short segment on benzene, which would be our chemistry portion, which will not be very long, I don't think. So yeah, so if you guys have any questions about anything that we discussed in the realm of probabilities, entropies, expected values, etc., any comments, let me know. But yeah, so yeah, entropy is an interesting topic, and actually has a lot of fields where it is particularly relevant. But yeah, if there are any questions, if there are no questions, then I would just touch on the last topic that we're going to be covering today, which is that of benzene. So, I kind of feel bad now since all this math stuff is how I sound like to my friends. Well, I hope I didn't sound too terrible. I hope it was mostly understandable. But yeah, so let me know if there's something a little bit rambly or a little bit intelligible. Yeah. I tried my best to make it a little bit just a little bit more intuitively understandable. In particular, this thing with entropy, because I feel like entropy seems like a very mysterious thing until you're related to statistics and probability. The sum of all the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Thank you so much for that information. I will save that for the geometry hierarchy lesson. I think I'm comprehending. Yeah, a lot of this stuff, in particular math, is really just about doing a lot of examples, and then I feel like it becomes a lot more intuitive. But I think at least just conceptually to understand, what is Bayesian updating, how do we introduce new information to a system, the difference between having a disjoint event with a non-mutually exclusive event, for example. I feel like those are just in general things that to keep in mind if you're in any field relating to statistics or relating to science, etc. I feel like those are good things to have in mind. So, yeah. So, I hope I made it a little bit understandable with some hierarchy examples. Yeah. So the last thing I want to talk about is a little bit on the molecular structure of benzene. So here we have a bunch of carbons, some hydrogens, and then there's also the formula written in here. So benzene has the chemical formula C6H6. So meaning that there are 6 carbon atoms and 6 hydrogen atoms. So benzene is typically represented as this planar ring structure with alternating single bonds and double bonds. So double bonds in chemistry are denoted with 2 lines, and single bonds are represented with a single line. And this basically means that in this particular type of bond, that they share 2 electrons or that they share 1 electron, basically. So these bonds are known as covalent bonds, meaning where an electron is shared between the 2 atoms. And this is what is holding them together. So the covalent bonds, again, are a type of bond where an electron is what is being shared between 2 atoms, and this electron basically holds the 2 atoms bonded to each other. And then we can actually describe this particular bond with something called the bond length, and this would be the distance between the 2 atoms that are in this covalent bond. So I take my bond and they're sharing an electron, and I look how far apart is this atom related to this atom. So how far apart is this carbon atom to this carbon atom? Why are some bonds double and some are single? So this has to do with how many electrons need to be shared. And in particular, in this ring structure, and this is what I want to sort of get to, it is not exactly the reality, because what this ring structure assumes is that some carbons have a double bond and some carbons have a single bond with each other. And these double bonds and single bonds basically change constantly all the time. However, this is actually not particularly the case. And how they know that this is not really the case and that maybe this is not the best representation of what this actually looks like in real life, it's because they actually measured the bonds between all of these carbon atoms. And because in a double bond you have two electrons shared, you expect them to be shared to have a shorter bond length, so that the atoms are actually closer together because they have more electrons holding them together. So typically this is the case. Double bonds are stronger than single bonds, meaning that the bond length is shorter, whereas single bonds is just one electron being shared, meaning that you expect this bond length to be longer. However, when they measured all the bonds in benzene, they found that they all have the same length. So how does this make any sense? How do I have some single bonds and some double bonds, but in reality they all have the same length? This makes no sense. And this is what is known as a resonance hybrid. So a resonance hybrid is a structure that is not fully represented by the drawing of by basically this structural drawing. It doesn't fully represent what's truly going on in the molecule, meaning that it is not particularly true that some bonds are double bonds and some bonds are single bonds. So this actually serves more as an average of the bonds that are shared between the carbon atoms. But in reality, what you actually have is a bit of a delocalization of these electrons that are being shared. And they're actually not localized. It's not like you have two electrons in a particular double bond and just a singular electron in a single bond. They actually are like somehow being shared all around this ring structure. And this has a little bit to do with quantum mechanics and so on, and some more complicated like pi electron situation. But in essence, this structure drawing gives us an idea of what this looks like, but on average, but however, when you actually go in and figure out what's going on and probe inside my benzene, you actually find that this is not the reality, and that these electrons are actually being shared basically all around the ring. So you don't really have either a double bond or a single bond, but kind of both at the same time. And they actually measured the bond length, and they found that the bond length was right in between what they would have expected between a single bond and a double bond, meaning that it's somewhere kind of in the middle between these two bonds. And that's actually all I prepared for benzene. But yeah, I'm not a chemist, so I thought this would be like an interesting thing to mention, that this is actually we're representing things graphically kind of sometimes ends up missing the point a little bit, or ends up missing some of the particular details a little bit. And yeah, I feel like that is very relevant for a lot of things. Sometimes when we try to simplify, we miss some of the things, like the very involved explanations of probability were not particularly captured in my presentation. But, sometimes all you need is the overall picture and not go into specific details. And yeah, and then I just show, so this is the one that you see from the opening. And I believe they probably included this in particular because it has kind of a cyclical structure, and I feel like with a lot of hard things, for example, endless aid, like things repeat over and over again, and just everything kind of seems like a loop, time travel and so on. And because it has a lot of H's, as we've seen, they really try to introduce a lot of equations and expressions with H's somewhere in there. And these are two other representations of how they sometimes will show benzene. These all mean the exact same thing. This is basically like organic chemistry. They don't even write the C's or the H's. They just assume if you have an edge, you have a C and an H. So that is how it works with organic chemistry. And then also this one with the circle in the middle kind of represents a little bit this, double bond, single bond conundrum situation. Yes. So are there any questions about this? I'm sorry if this was not like I didn't add much more. I just felt like I don't know if there was much more that I wanted to say about benzene. It seemed like a kind of a little bit of the oddball in terms of all the things that we analyzed, at least to me. It definitely seemed like a little bit different than everything else that we have discussed. Yeah, organic chem, the bane of my 11th grade class. So true. I honestly, actually, yeah, I actually did quite a little bit of chemistry in high school, but, it was a lot. It was a lot, especially organic chemistry. Very true. Then this model is wrong, but you're just too stupid for the real thing. My teacher said every other lesson. Wow, that's really mean, but I guess at least in this particular drawing of benzene, that is a little bit true. But yeah, please write down any questions. I will just touch on the last thing, which is not really me presenting anything, or more so presenting a question, which is I have no idea what this equation is. I asked around on Twitter. I asked like ChatGPT. I looked it up like 100 different ways, and I really cannot figure out what this equation could be. It doesn't help that it's more so an expression and not really an equation, right? There's no equal something. So I have no idea what this is. Definitely seems like a weird, like, abstract math expression. But yeah, so if anyone has an idea what this could mean, what this could be, please let me know. But yes, I have no idea personally. But yeah, that would be it from all the things that I wanted to present today. And yeah, so true. Maybe they put that as a challenge, as a joke for anyone to try to identify